So for problem number 10, part A, we've got a semicircle of charge. We're given the density and the radius, and we need to determine the total charge on the semicircle. So this comes from the equation that the linear density is equal to charge over length, and the semicircle can turn into or the length of the semicircle can be determined through our equation that length of side is equal to r times the angle. And since we know that it's half of a full circle would be 2 pi. In this scenario, it would equal pi. And so our equation would be lambda times r pi is equal to q, and therefore q is equal to 4.0 times 10 to the negative 6 times the radius of 0.2 times pi, and you would get an answer of 2.51 times 10 to the negative 6 coulombs for A. For part B, we need to determine the magnitude and direction of the electric field at the center of the semicircle. So the way we do these problems, as always, is we start by taking a small piece of the semicircle, and that would be dq. We can call that small piece dl as well. And then we see how that charge, it says it's a positive charge, how that charge is going to look if it is at the origin. In this case, it goes out of the positive charge, and it's going to look something like this. We always want to check with the opposite side of our figure because we're working with symmetric objects here, and the point of using symmetric objects is that we can see that a component will end up canceling out, and in this scenario, it'll end up being the y component. We can see that as the electric field of the bottom has a component pointing up. The electric field of the top has an electric field pointing down. And so that gives us zero electric field in the y direction. So we can write that out here. The electric field in the y direction is equal to 0. So the electric field in total is going to be the net electric field in the x direction. So the next thing we're going to do is we are going to identify an angle, theta, and we're going to use the x component, which is cosine theta. So since we're working with subsections of our ring, we are going to take a small portion of the electric field using a small portion of our charge, and that's going to be part of our equation. The radius here is nice because it's actually the radius of the circle, so capital R squared, and since we're only working with the x component, it's going to be cosine theta. The next step that we are going to do is, since they are giving us the linear charge distribution and we don't have Q, then we're going to have to convert our dq in this expression to include lambda. So just like we saw in part 1, lambda stays consistent throughout. So even if we got a little portion of the charge from a little portion of the length, we would still get the same charge distribution, and so dq is equal to lambda dl. And our new substitution would include that, lambda dl over r squared cosine theta. And then from there, we just need to figure out dl is a known expression, and we've got this variable, or dl is a variable, and so is so is our theta value. So we need to find a way to condense those into each other. We already did it over here. L is equal to R theta. So if I just took a portion of dl, it would equal r d theta. So I'm going to make the substitution of r d theta in for dl. By doing this, I can integrate over, let me pull the d theta out to the very outside of the expression. I can integrate over theta because I have cosine theta. I can also reduce because the r's can reduce down to 1r in the denominator, and cosine is an easy function to integrate. So let me integrate, leave my constants out. I need to think about my limits. I'm starting here at 90 degrees, or pi over 2, and I'm working my way all the way down to 270. 270, so I've got 90 degrees at the beginning, up to 270 degrees, and when I integrate, I get E is equal to lambda k, doesn't matter the order, cosine theta is sine of theta, and I'm going from 270 to 90. Sine of 270 is -1. And sine of 90 is +1, so -1 minus 1 is equal to -2, and I get an electric field of -2 lambda k over r. That's not my final answer. I still need to plug in my values to solve for the magnitude and direction. It tells me that the value is negative. I'm creating an electric field from a positive charge, so it actually should represent a positive magnitude, and also the direction is to the right. So let's just plug in our values. Lambda is 4 times 10 to the -6. K is 9 times 10 to the 9. And R is 0.2. When I plug all those values in, I get 360,000 newtons per coulomb. And that matches 3.6 times 10 to the 5th newtons per coulomb. So that's going to be my electric field. Direction is to the right. Again, I got a negative when I did my integration, but when I looked at it, I knew it needed to be positive. So it might be because I was going from in the wrong direction, from 90 to 270 when it should have been 270 to 90. Regardless, it's important to check your answer with the diagram. Okay, so let's do problem C. Determine the magnitude and direction of the electric force applied by the semicircle on a test charge Q. Force is just equal to EQ. So all it's going to be is 360,000 times 3 times 10 to the -9. And that will give me a value of 0.00108, or about 1.1 times 10 to the -3 newtons. The direction is going to be right because it is a positive charge, and positive charges go away from the positive rod. And then D, if the test charge is released, describe its motion for a long time after the release. Again, there is a force, and therefore it's going to have an acceleration. So it's going to move to the right with a high velocity. With increasing velocity, because it is accelerating to the right, but that acceleration is going to decrease as the distance decreases because it's proportional to force. And so the acceleration with increasing velocity and decreasing acceleration.